A pulling force F is applied to a block along two directions. First horizontally, and then 60 degrees with the horizontal, as shown in the following figure here. The magnitude of the force is kept constant. In both cases, the block is in equilibrium and moves at a constant velocity. What is the kinetic friction constant? So it would probably help if we first start by drawing some free body diagrams. So this dot is going to represent the box, and this will be in the first case where the force is applied horizontally, directly horizontally. So we have the force. Of course, we have the normal force and the force of gravity, or mg. And then opposing the force, we have the force of friction. And then that is the first scenario. In the second scenario, the force is moving at a 60-degree angle. So this is the normal force, and that's the force of gravity. They're always there. And then here we have the pulling force, and it's at a 60-degree angle to the horizontal. And opposing that, we have the force of friction, which opposes this force. And now we have the second scenario, which is the 60-degree force, and we have both scenarios. Now to start, let's look at the first one. These two are a pair, so we know that the force minus the force of kinetic friction must equal the mass times the acceleration. It's the net force thing with Newton's second law. Now there is no acceleration, so this whole side of the equation is 0. So you can just set that equal to 0. So from this, we get that the force is simply equal to the force of the kinetic friction. So from the first scenario, we know that the force is equal to the force of kinetic friction, which is equal to the coefficient of kinetic friction times the normal force. And in this first case specifically, the normal force is equal to mass times gravity. You can figure this out using the same thing as before, where you have the normal force minus the force of gravity is equal to 0, since it's moving at a constant velocity and there's no acceleration in the y direction. And then we can substitute that in, and we get that the force is equal to the coefficient of kinetic friction times the mass times the gravity. And that is what we can get from this first one, in this first free body diagram. So I'm going to rewrite this here. From the first free body diagram, force is equal to coefficient of kinetic friction times the mass times the gravity. Now let's look at the second one. We can break this 60-degree force down into its components by using decomposition of vectors. So the horizontal component, we have the force times the cosine of the angle for 60 degrees. And in the vertical direction, we have the force times the sine of the angle of 60 degrees. You can use basic trigonometry to find this, where this is the 60-degree angle. And now we have broken down the pulling force. So let's start with the vertical equation. We know that the normal force and the pulling force from the angle must oppose this force of gravity to keep it in dynamic equilibrium. So we know that this force, the pulling force, at an angle of 60 degrees, the vertical component of the pulling force, plus this normal force, must equal the force of gravity. And this is a fairly important second equation here. And from here, we can solve for the normal force. So from that, we can derive that the normal force is equal to the force of gravity minus the vertical component of this pulling force here. Okay, so now we've got this, and you'll see why this is important in a second. Now for the second part, we're just relating these two again. It's the horizontal component of the force and the force of friction, and they have to be equal to each other because the object is not accelerating at all. So here we have it. And again, the force of friction is equal to the coefficient of kinetic friction times the normal force. So now you can probably see why we solve for the normal force here. This way we can substitute the normal force into this equation and substitute everything back in over to here. So after all of that, we get that the force times the cosine of 60 is equal to the coefficient of kinetic friction times the normal force, where the normal force is the force of gravity minus the vertical component of the angled force here. So now we're down to this equation, and can solve this pretty soon. Now remember this force that we solved for from the first scenario? We can also plug that in and substitute that into these two here, this and this. It's going to get a bit messy, but we're going to be able to clean this up really soon. So, the coefficient of kinetic friction times the force of gravity times the cosine of 60 on the left hand side is equal to the coefficient of kinetic friction times the force of gravity. I'm going to remove this from the parentheses. Times the coefficient of kinetic friction times the force, which has another coefficient of kinetic friction, times the force of gravity, times the sine of the angle, or 60. So now we have this really messy equation, but we can simplify this by simply canceling a few things out. So we notice that each component, each part of the equation has this, the coefficient of kinetic friction times the force of gravity. So we can just go ahead and divide everything out here. So all of these cancel. So we get that the cosine of 60 degrees is equal to 1 minus the coefficient of kinetic friction times the sine of 60 degrees. Again, you replace this with 1 as it's divided by itself and leaves you with 1. Now I'm going to erase everything else so that we have a little more space to work with. So I'm going to get rid of all of this. And we're left with this neat little equation right here. And now from there it's just simply solving everything for the coefficient of kinetic friction. So you do this by moving the one to the other side, and then you can conclude that this is equal to minus cosine 60 minus 1 over the sine of 60. And then that can be simplified into the final answer that the coefficient of kinetic friction is equal to 1 minus the cosine of 60 divided by the sine of 60. And right now it's still just an expression, but we can substitute the cosine of 60 degrees, which equals 1/2, and the sine of 60 degrees, which equals square root of 3 over 2 into this equation. So I can get this equal to 1 minus 1/2 is 1/2 over the sine of 60 is square root of 3 over 2. And then now, if you simplify all of this, you should get that the coefficient of kinetic friction is equal to the square root of 3 divided by 3. And that is going to be the final answer here.